I will begin with a word of prayer, as to annoy the internet. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just pray that you help us to just say some reasonable things about algebraic topology and just make a little bit of progress on the topic of homotopy. Lord, in your name I pray. Amen. So, I'm somewhat prepared today. We'll see how it goes. Probably goes before the fall, right? Alright, let's see here. So definition. Excuse me. If f from x to y is continuous, then bracket f like this is the equivalence class, or homotopy class to be more clear, homotopy class of f. And what that is, it's all continuous g from x to y, such that what? Right.
Or homotopic.
Yeah, such that g is homotopic to f. So the family of all such homotopy classes is denoted, in other words, this guy is an element of this guy. Okay, so all homotopy classes oh no, but we'll be confused with the Lie bracket. No. Not really. Okay. So theorem 1.3. We have F1 and also F0. Both of these guys are maps from X to Y, and we're given G1 and G0 maps from Y to Z. Both of continuous all around, all right? And then here's the thing, if F naught is homotopic to F1, and if G naught is homotopic to G1, sorry, I said G1 is homotopic to itself, that was stupid. So G naught homotopic to G1, then of course you can form compositions, right? So you can look at like G naught composed with F naught, and guess what? That's homotopic to, you guessed it, G1 composed with F1. So of course, what does that tell us? The homotopy class of G composed with F naught is equal to the homotopy class of G1 composed with F1. All right. All right, so proof. All right, so here we go. Suppose, so where we're going is to try to explain the basic properties of homotopy today, and I think I talked to you guys too long about other stuff, so we probably won't get to it. But we were going to get to what's a cone. But anyway, we have today, and I set aside today and next day to talk about homotopy, cones, and path connected. Path connected is actually a pretty short bit, so I think we'll still have time to do everything between today and next time. And then you guys will be on track for next week, right? So Tuesday you do the find spaces, and Thursday you're doing...
The homotopy groups?
What was it? Was that it?
Right?
Whatever comes after a find space is the... oh, that's right, yeah, the homotopy groups. The fundamental groupoid. Yes, next Thursday, Nathan will be talking about the fundamental group. So basically your goal in those days is to say the most interesting part of those sections in the time we have, right?
Wait, so I'm just doing that one day?
Yeah. So.
Drink a lot of coffee.
So here we go. Let me try to make sure I don't put you guys behind schedule. So suppose F is a homotopy of F naught, to F1. Let me find a marker. Less weird color. That thing won't show up. And suppose G is homotopy of G0 to G1, right? So of course what that means is what? F is actually a mapping from what? From X cross I to Y, is that right? And G is a mapping from what? From Y cross I to Z, okay? Such that it's continuous, and if you plug in 0 for time, you get G naught. For 1 for time, you get G1. And likewise over here, plug in time 0, you get F naught. Plug in time 1, you get F1. Excuse me. He says, so first what we're going to do is show that first show that G naught his goal to show, he first wants to show that G naught composed with F naught is homotopic to G1 composed with F naught. Alright, so how's that go? He constructs the following homotopy, H, of x comma t equal to G, alright, of what? G of F naught of x comma t. Now, is H continuous? Excuse me. First of all, H is certainly in the right kind of thing, right? It's x cross I to z. Is that clear from the formula? I mean, G has output of z, right? F naught of x is in it's in y. What's that?
Yeah, it's in Y.
It's in y. And then that's what G is. That's right for that. It's continuous because it's the composite of continuous things. And what else do we need? Oh, we should plug in. What happens when you put in 0 here? What do you get? Right. And
So it's just going to be G naught of F naught of X.
okay. Oh, excuse me. Yeah, you're right. That's like you said. That's G naught of F naught of X, right? By the definition of G being a homotopy. And when we plug in 1, what do we get? That should be G1 of F naught of X, right? By the definition of homotopy. And so this is a homotopy, just like it says, of this and that, right? You follow? Any question, Nathan?
Yeah, isn't it a homotopy between G naught of F naught and G1 of F1? Down there you have G1 of F naught.
No,
No,
to
we're
start
doing-
with,
we're doing part way
we
first.
prove this first, and then,
Oh, okay, so
It's not-
it's by transitivity.
yeah, I think so.
Okay.
And then the next thing he does is,
So G1 of F naught is...
yeah, here I'll write, he says K, he's like, if you look at K, which he's going to say is G1 composed with F, I'm not sure what he's saying yet here. He says, next observe that K, G1 composed with F naught, homotopic to G1 composed with F1, where, how does he define K?
It'd be like G1 of F.
Right, yeah, it's the composite of G1 and the homotopy F, big F. And then what you said, then we use transitivity, right? Because so this gives us, this is homotopic to that, and then that is homotopic to that. Consequently, by transitivity, this guy is homotopic to that guy, which is what we're trying to prove. So you're right, that was not the complete proof. That's like a midway step, and then construct yet another homotopy, like Daniel said.
Okay.
Excuse me, G1 goes without. Does that make sense? G1.
Well, that bothers me. It should be parentheses G1 cross ID composed with that.
I think you're right about that. So, or to be more specific, K of xt equals to F. Oh, excuse me. What is it?
G1 of f of xt.
Yeah, this is a little bit freewheeling, isn't it? I mean, he writes that there, but I think that's with the understanding he means this, right? Is that well?
Oh no, that's fine. I was thinking of it backwards.
Oh, okay.
It'd be if it was the other way around that you'd have to.
I was about to be kind of like
Yeah.
shocked because
Because it's you have the direct product in the domain, so that's applying to the image, which is
That's
fine.
fine.
Yeah.
Okay. So we're good.
So I was wrong.
You're fine. Let's see here. Wow, Rotman finally said something incorrect. No, not today. Sorry, guys.
One day.
One day we'll find it. We'll find an error. Let's see here. I mean, I'm sure there's. If I was to print out the errata page, what? What's this about? Oh, Angry Birds, Mighty Eagles, waiting with you for your free ticket. Do I really need to get a... kids in their games. I'm gonna have to... Let's do the Angry Birds. It's cluttering my phone. Alright, I'm just gonna read a few things, and I'll start writing again. First of all, he points out that homotopy is a congruence on the category of top. So, that's here's a notion of equivalence, an equivalence relation, right, over the category of topological spaces. And so this gives us a corresponding quotient category. And so it says, by definition, the quotient category just described is called the homotopy category, and it's denoted h-top. It goes on to say that all the functors, T from top to A, where A is some algebraic category, abelian groups, groups or rings, mostly, you'll have the property that if F is homotopic to G, then T of F is equal to T of G. So, let's see here. What do I want to say? So what does it mean to have two spaces to be of the same homotopy type? You know what it means for two spaces to be homeomorphic, right? It means that there exists a bijective map with continuous bijection with continuous inverse, right? Homeomorphism. So this is homotopy, sort of a homotopy version of that, and so let's talk about that. We have F from X to Y, homotopy equivalence, which is called what elsewhere, Nathan? You were telling me?
Oh no.
Or this is...
I was talking about when they said equivalence of categories. Or no. I was talking about they called isomorphisms equivalences.
Ah.
This is completely different concept.
Oh, okay.
And actually this is more analogous to actual equivalence of categories.
Yeah, okay.
Because you see here, Well, maybe I should let you write it out first.
Okay. If there is g from y to x, right, and continuous, and let's see here, f composed with g is homotopic to something, g composed with f is homotopic to something. What do we have to put there?
One's the identity on y.
Mm-hmm.
First one's the identity on y. The one's the
Right.
identity on x.
The identity on x, right?
So,
So they don't have to be in homeomorphism, they have to have equality, right?
yeah.
And then that would suffice to, I think that would suffice to make it a spaces to be homeomorphic, right?
Yeah.
Yeah, yeah.
But so, replace continuous functions with functors, and replace homotopic with naturally equivalent,
Mm-hmm.
so natural isomorphism. And you have the definition of a categorical equivalence.
Hmm.
So categorical equivalence is very similar to this notion of homotopy equivalence.
Hmm. Interesting. Let's see here.
And there's a lot of interesting examples of that, which I'll probably point out when I do the natural transformation chapter.
Okay, good. Let's see here. I guess I have forgotten to tell you the punchline, right? If such an f and such a g exist, then what?
Then x and y are homotopy equivalent.
Right, x and y
Are of the same homotopy type.
of the same homotopy type, right? For the most part, this section is just a litany of things which are true about, you know, basic facts about homotopy and homotopy type. Yeah, for example, in definitions, but definitions are important. Let's see here. I mean, you know that. You signed up for another semester of this, I guess you must know the definitions are important. So let x and y be spaces, right? Those are topological spaces. He just says spaces, right? So you need topological spaces. And brevity is the soul of wit, right? I read more. Y not an element of y. Then the function c from x to y with c of x equal to y naught for all x and x is what? This is the so-called constant map, right? You know that. He says it's the constant map at y naught. All right. A continuous map f. All right, from x to y. So f from x to y, continuous, is null homotopic. It's null homotopic if what?
Homotopic to a constant.
Yeah, if there exists constant map. What'd you say?
Such that f is homotopic to c.
Right. So this is the notion of a null homotopic map. It's homotopic to a constant map. Now, the next theorem is kind of striking. Theorem 1.5. Let C denote the complex numbers. Right, and let sigma sub p be a subset of the complex numbers. It's a circle, radius, row, right? In other words, it's basically z such that the modulus of z, see what you've done to me, Nathan, row. Equals, right?
Wait, did you say norm initially?
I said modulus, but I wrote norm. I was like, del bar.
Oh.
Sorry.
Well, no confusion in the complex case.
Yeah, I know. Okay, and then it says let f, I guess it's supposed to be a row, not a p, sorry. Let f row upper n be a mapping from the circle, radius rho, alright? To the complex numbers without zero, right? He wants it to be the restriction of the map. Z maps to z to the n. Alright, the nth power function. That's just set up, alright? Then here's punchline. If none of the maps f row to the n is null homotopic, n greater than or equal to 1, row positive, alright, then the fundamental theorem of algebra is true. Fundamental theorem of algebra being that every non-constant complex polynomial has a complex root. There. All right. Let me gather my strength after writing that. You guys can't get me too tired today. I still got to teach trig substitution after all this. As you know, trig substitution requires all my mental facilities. Okay, it's not entirely true. Trig substitution is fun. So there's that. Where was I? When do we end? 3:30, right? Because I teach at 3:45? Yeah, that's cool. Okay, so. Sorry, I'm trying not to infect you guys. I don't believe I'm contagious anymore, but my wife claims otherwise because she just got sick. Let's see here. Where was I? Oh, okay, so. So I'll start the argument here. Proof. I mean, this is kind of a shocking result, right? I mean, isn't it weird that the fundamental theorem of algebra has anything to do with null? I guess it's not too surprising if you've studied this before. But here it is. So you consider complex polynomial with coefficients. You look at g of z, z to the n, plus a to the n minus 1, z to the n minus 1, plus da da da, plus a1z, plus a naught. All right? And he says you choose the row equal greater than the max of 1 and sum I equals 0 to n minus 1 of the modulus of the coefficients, a sub I. All right? And define f from that circle, cross the unit interval to the complexes by, what do we do? So he says do f of z comma t equal to z to the n plus the sum I equals 0 to n minus 1 1 minus t, a sub I, z to the I. Now he claims it's obvious that f provides a homotopy of the restriction of g to the circle and fn of rho. He says that this provides a homotopy of g restricted to this and f rho n. Let's see if I believe that. What do you guys think?
Well, it looks continuous.
Continuity, yeah,
Yeah.
as usual.
And,
It's a polynomial. So that looks good.
yeah. And f of z0 is just z to the n. Oh wait, no. It's g of z.
F of z, comma 0.
It's just gonna be g of z.
Is g of z, right?
And f of z.
And we're
comma
assuming,
1.
of course, that the input to z is from the circle.
Right.
I mean, the domain here. This is for z, comma t, an element of this guy across this guy. Right. So, yeah, that we get g of z where z is taken from the row circle. So when we plug in t equals 0, we get g. When we plug in t equal to 1, what happens?
We get z to the n, which is just
Exactly.
fn rho. Or
No. Oh, because t equals 1 knocks that out. We're just left with z to the n for z in row p, which is exactly the definition of that. So this is a homotopy. Okay. He says, if we can show that the image of f is contained in the complex plane without 0, of the deleted plane, that is to show that f of z comma t is not equal to 0, I don't know what that, where's the if?
I think what he's saying there,
I don't see a then following that if. I'm missing
Like
this.
that whole
He's saying
that
it's
whole-
obvious that this is a homotopy if we can show this.
Oh, okay.
because essentially, like this whole paragraph, I think he's just showing that it's well defined that the image is actually going to be in the units of c without 0.
Right, because
Right.
we actually need to show that it maps to c minus 0.
So
Yeah,
we
and that's
need-
what he's doing in
We
that
need
paragraph.
f is going. Now, why do we need that? Sorry, I missed something.
Because, well, g,
You said it has to map to c without 0?
yeah, well, for one, the f and rho map to c without 0,
Oh, right.
and the g as well, I think. Yeah, the g as well.
Why would the g not hit 0?
If the norm, if the modulus of z is non-zero, then the modulus of z to the n. Oh wait, no. Oh, never mind. I think it has to do with
It must have to do with the construction of rho.
with the construction of rho.
So that's technical. Oh, I guess that's what this inequality is here, huh?
Yeah, I guess I'll show explain.
But rather than show it directly, he uses contradiction, right? He's like, so suppose towards a contradiction that you did have f of z comma t equal to 0, right? For some t. then z to the n.
And there's some t where that's there's some t where that's true.
Do you get this? Oh, for some t and some z, then z to the... I mean, is he saying there's a particular choice of t and...
Such a choice exists.
Well, it's you're trying to show that f of z comma t is not equal to 0 for any zt, so that's just the negation of that.
Right.
There exists a z and a t such that f of zt is 0.
Yeah, I guess I'm trying to... I'm grappling with why does he get to write this at the moment.
Well, that's f of zt equals, that's a different way of writing f of zt equals 0.
Yeah, that's the definition he uses. He was just moving the summation
Oh,
to the...
okay, I'm an idiot. Yeah, he just solved this for 0.
Yeah.
Okay, got you guys. Got it.
But it's z to the I. You wrote rho to the n minus 1 at the end. At the end of that, it's z to the I.
Oh, thank you. I just
Yeah,
skipped lines here. Sorry about that. Yeah, AI, ZI. Thank you. And then he's like, triangle inequality gives us rho n less than or equal to...
Right, the norm of the sum is...
So that's the norm of z to the n.
Sorry.
That's okay. And then what do you say? That's less than or equal to...
Well, rho to the n is equal to z to the n.
Right.
Or norm of z.
Yeah, excuse me. That's just equals, right?
Right.
But then we can use this to... And the property, the triangle inequality.
Mm-hmm.
So that's the sum I equals 0 to n minus 1. I guess you should have... I was about to say you need absolute value there, but I guess 1 minus t is obviously
Right.
positive, but you do need absolute value here.
Mm-hmm.
And then...
Rho to the I. Well,
right, because... Yeah. Again, using that... Here, he's... This guy, right? I mean, you can... Thankfully, none of the nasty stuff we were talking about before we turned the camera on happens here.
yeah.
The stupid... the coefficient of the algebra enters in the submultiplicative case here. Yeah. I digress. Where were we? And then he says this is less than or equal to what?
So now he's just saying that 1 minus t is
Oh.
less than or equal to 1.
Drop the t because it's positive, so you just And then what? What's here?
Since I is less than n minus 1 each time, he's gonna, instead of writing rho to the I mean, it's gonna be less than the same thing, but with rho to the n minus 1.
And he can do that because he chose rho to be greater than 1.
Mm-hmm.
So it goes back to our condition for choosing row. So that's, run out of space here, less than or equal to sum I equals 0 to n minus 1 modulus of AI rho to the... So you guys understand that?
Mm-hmm.
Yeah.
Then you can cancel rho to the n minus 1 on both sides of that inequality.
Ah. So that implies that rho is less than or equal to the sum I equals 0 to n minus 1, the modulus of a sub I.
And that's a contradiction.
Which is a contradiction to the construction of rho. Whoa. So apparently, f of z comma t is not equal to 0. Which says what? That it's a homotopy? Okay.
Mm-hmm.
So then, assume that G has no complex roots, right? Define another homotopy G from the circle, radius rho across I, to the deleted complex plane by what? So G of Z comma T equal to G, where that's the complex polynomial, right? And then 1 minus T times Z. Is that it? So we're assuming that G has no complex roots, right?
Right.
Now, is it clear that that's a homotopy then? I mean, no roots in Z, no roots in C means that this image is in the non-zero complex numbers.
And then G of Z, 0 is going to be little g of Z.
Just G of Z.
Right, and G of Z1 is going to be G of 0.
G of 0,
Which is constant.
right? So of course that's equal
And
to...
it's the composition of continuous functions.
right, it's a composition of continuous, so it's continuous. So this is definitely, this provides a homotopy between G, homotopic to the, the constant at G0, G of 0, right? Is that the right notation? I forget.
Yeah.
He said visibly, he uses this a few times in this section, he says visibly.
Clearly. Obvious.
Visibly. G, so is that a way of saying clearly without being held to the stigma of using clearly?
Yes.
G restricted to the circle radius rho, it's hilarious. Is homotopic to K, where K is what? Constant function at A naught. Oh, G of 0 of course is A naught, right?
Yeah.
Yeah, okay. So then what? Therefore, G restricted to the circle radius rho is null homotopic.
And this F is null homotopic. F and rho is null homotopic.
By transitivity, F rho to the end is null homotopic, and that contradicts the hypothesis. None of the F rho to the end are null homotopic.
I hope that later will show that it's true. That the hypothesis is true.
Oh, right. So yeah. And I guess this proof even kind of gives you a sense of when it's true, you get, a result. Anyway, let's see here. So let's see here. Next, we look at conditions, equivalent conditions from null homotopy, and continuous maps, and so I think that's actually a pretty good place to start next time. We'll start at basically right past this proof we got to, and so what we'll do next time is we will do the the comments about extending maps, and then that gives us the condition between null homotopy. Actually the theorem is for n spheres, so like F is a null homotopic map from the n sphere to another topological space Y, only if it can be extended to a continuous map from the n+1 disk to Y. or then step 3 is a somewhat technical condition. And then that allows us the terminology we need to talk, at least, I mean, that's part of that's what's involved in talking about cones and convex. There is one thing I don't understand as I was reading, guys, maybe you can tell me before I leave. He says over here somewhere, he says that the, I must be dumb, I don't know, where was that? Somewhere he talks about convex maps versus contractible maps, you know? And, I mean, one of the things he proves eventually here is that for every space, the cone is contractible, right? You think of the cone basically as just taking your space and attaching the unit for an interval of every point. But then all those separate unit intervals, you attach the endpoint of them together as a single point. That's a cone. Of course, he makes that explicit here, but somewhere in here he says that the hemisphere is not convex, and I don't.
Yeah, I noticed that too.
I don't understand how a hemisphere would not be convex.
Yeah.
There's something I don't understand there. I gotta look at the errata, but it seemed to commit to it. But I mean, if I think about a hemisphere, I think about a half circle as a prototypical one. And golly, it seems like to me any 2 points are connected by a line. That line is inside the. I mean, I just don't see how that's not convex. You know, if I take any 2 points in the space, then the line which connects those 2 points is in the space again. I don't know, I gotta take a closer look at his definition of convex, see if I missed something, but I think that might be a typo. Let's hope that's a typo. Otherwise, I have some like deep and subtle misunderstanding of what it means for space to be convex, which would be troubling to me. It wouldn't be without precedent for me to have a misconception about this sort of thing, but I hope I'm wrong. I mean, I hope he's wrong. Just this once. Makes sense.